is I'm gonna put together an example of calculating a confidence interval for the mean. Okay, so let's say we have a population, mu, mean for the population, and sigma for the population. Generally, these are unknown, but I'm going to make believe I know them. And I'm going to say that mu is equal to 300, and sigma is equal to 10. So standard deviation is equal to 10. The population mean is equal to 300. I know I'm talking about the population because I'm using mu and sigma instead of x bar and s. I'm using Greek letters. So the population distribution would look something like this. The center would be at 300, right? Because that's the mean. And the people within this distribution, they would be normally distributed. More would be closer to the mean. Fewer and fewer would be far away from the mean. They would be normally distributed. And sigma is equal to 10. That would indicate to us that 95% of the population here, of the people involved here, are between 2 standard deviations above the mean and 2 standard deviations below the mean. In other words, they would be roughly between 280 and 320. Perfect, exactly right. So, and then we could even say, if I go only 1 standard deviation below and above, I would have 68%. That's our empirical rule. In reality, we know that when we're talking about 2 standard deviations, that, in other words, 95% of the population between these 2 levels, it's not really exactly 2. The empirical rule is really an estimate, right? It's really 1.96 standard deviations below the mean and 1.96 standard deviations above the mean, right? If you look it up on the Z table, you'll see that it kind of that it looks like that. And the reason why we know that from the Z table is because this area in here, right, and this area over here, they must each contain 2.5% of the population. And why do we know that? We know that because 95% is between these 2 points. That leaves 5%. But the normal distribution, if it's truly normally distributed, then it's symmetrical. So half of it's going to be at the top, in the top tail, half of the extra people are going to be in the bottom tail. The only problem with this is that we never really get to see this. We can describe this, but we don't ever get to see it because we never actually measure the entire population in most typical studies. However, we will occasionally take a sample because we want to know what is mu. This is our real view. What is mu? What is sigma? We don't know what they are, right? So we take a sample to estimate what they might be. Okay, so now if I take a sample, the size of the sample is going to impact how well we know the mean and the standard deviation, right? So what I'm going to wind up with, if I take a sample, I'm going to say of size, I'm going to say a sample of size, say sample size of 100. I take a sample size of 100, and I say to myself, what is the mean? And I sample 100 people, what's the mean that I get? And X bar turns out to be, from this population randomly selected, if I were really lucky, maybe I get 300, hit it right on the nose. But most of the time, that's not going to happen. Most of the time, I'm going to get, maybe I'm going to say 295. Okay, so I'll make it 296. Okay, so now, the other thing I'm interested in, what's the standard deviation of this population? I'm going to say that that's S in place of sigma, S approximates sigma, S is equal to, let's say that it comes out being equal to, let's say, 11, for argument's sake, right? It's close, right? Not exactly the same, but it's close. And this looks like a pretty good approximation of what this distribution is, what this is. And that generally will happen when you get a big enough sample size. 100 is a pretty big sample size for a study, right? So we usually get a pretty good picture of where we are when we do that. Okay, so now the problem is that I don't actually know what these are, right? All I know is I got 296. I don't know if that's a good estimate or a bad estimate. I'm looking at this. If I know it's 300, I can tell if it's a good estimate or not. If I don't know it's 300, I can't tell how close I've come to the actual mean. It's just pure guesswork. So I need to be able to describe how accurately or how likely I am to have come close to what the actual mean is. So it's based on what we understand about how samples operate. We know that if we take repeated samples of size 100 from a population that's not known, the sample means themselves would be distributed normally, right? They'd be a normal distribution, but and the middle of that normal distribution of all the sample means would be the same as the mean of that population. Well, I don't know what that is. So I'm going to put 296 here instead of 300 because I don't know 300, right? The big difference is, and why is that? Why am I going to get something in the middle? The reason I'm going to get something in the middle is because if I sample 100 people, sometimes I'll get 296, sometimes I'll get 311, sometimes I'll get 299, and so on and so forth. Half the time I'll get something below the mean, half the time I'll get something above the mean, and they're going to be distributed normally like this. The main difference is that the standard deviation when I calculate it comes out to be 11, right? Well, that's an approximation of population standard deviation because the people that I sample, those 100 people, are distributed. The range of those values is going to be similar to the population because they came randomly from the population. But when I take samples over and over and over again, I'm going to get, especially with a big sample like 100, the values I'm going to get over and over and over again are much closer to the mean of the population than any individual person that I would pick, right? So the distribution now is also going to be normal, and I'm also going to get 95% of the possible outcomes for calculating a mean from a sample of size 100. 95% of the outcomes would be between two standard deviations below and two standard deviations above. But the standard deviation for repeated samples, we give that a new name. We call it the standard error. And we calculate it by taking the standard deviation of the population, sigma, and divide it by the square root of the sample size that we're using. Well, the problem is we don't know what sigma is. So we substitute for sigma, we substitute S, because that's what we know, right? We know standard deviation of all the people in our sample, and we know it should be close, so we're going to substitute that and take the square root of that. So what does that equal to? That's equal to 11 over the square root of 100, which is 10, right? So it's equal to 1.1. Okay, I'm going to make this number 298 instead of 299. Okay, so it's 1.1. So I know two standard deviations below the mean is going to be 295.9. Am I right? I think I'm right. Yeah, I'm right. No, 295.8. Right? So it's going to be two standard deviations. Is going to be 2.2 subtracted from 298 is going to be 295.8. You agree with me?
No,
okay, good. All right. I just want to make sure my math. Just want to make sure my math is right.
My question is more semantic.
Okay.
You call that also standard deviation?
I call it.
Working with the standard error.
The standard error is a standard deviation, but it's a standard deviation not of the population, but of the repeated samples of size 100. The mean that you would get for repeating the sample of size 100. This time I get 296. This time I get 301. This time I get 299. If I took all of those repeated samples, this is the standard error is the standard deviation of that, the distribution that's created by those numbers, not the population. Yeah. Well, standard deviation, right? Standard deviation, though, is the standard deviation of the population, right?
You have a standard deviation of the sample.
I'm sorry, where's that?
The one that you use is the standard deviation of the sample.
Oh yeah, this approximates the standard deviation of the sample approximates the standard deviation of the population. That's why I just substitute. Yeah, yep. So that we call standard deviation. We try and stick to that name for the actual population and standard error for our samples. Okay, so now it's interesting. We now, and this is going to be 300.2, right? So we know now that we can speculate now that based on what we see here, assuming that we got pretty close to the sample mean, that 95, let's say we got lucky and we got exactly the sample mean. Well, if we got lucky, got exactly the sample mean, we could say 95% of our results for X bar would be between 295.8 and 300.2. The problem is that we don't know what mu is. It's 300, but we don't know that for a fact, right? So instead, what we say to ourselves, well, when we get this number, there's a 95% chance that this number is within 2 standard deviations of the real mean. In other words, 300, let's say it was 300. Well, this should be within 2 standard deviations of that real mean. So instead of looking at it as if this were the actual mean itself, we say to ourselves, X bar was equal to 298. However, we're 95% sure that it's really between 295.8 and 300.2, between those two numbers. How did I get that? I got that from the formula that we learned. X bar plus or minus the range of numbers that represents 2 standard deviations above and below. Except I'm not going to say you remember 2 is not accurate. So it's really the range of values that represent 1.96 standard deviations above and below the mean that I calculated, times the standard error, right? Which in this case happens to be 1.1, right? So 2 times 1.1, 1.96 times 1.1. So X bar is 298. Call this 298. 298 plus or minus 1.96 times 1.1. Okay, so let's calculate what that is. Okay, my calculator here. Okay, and what was it? 3.39? 3.29? 3 point, no.
Wait.
I'll do it also. Clear. 1.6 times 1.1. Yeah, this number I get 2.156. This is 2.156. Now I still have to add and subtract that from 298, right? What do I call that? What shall I call this number I'm adding and subtracting? I'm going to give that a new name. I'm going to call that the margin of error, right? Good name, because it's plus or minus this, right? It's, if I told you this holds 12 ounces plus or minus 3 ounces, right? That 3 ounces would be the margin of error. So now I'm going to take that number and I'm going to subtract it from 298.
Oh, I was doing the whole thing.
Oh my goodness. Okay, you were way ahead of me. Okay. I just erased that. 1.96 times 1.1 equals this. I'm going to put that into memory. Then I'm going to take my 298 minus 2.156, and my margin of error is 295.8. I'll call it. That's the same thing, almost the same thing, right? No big surprise that it's almost the same thing because I did 2. I multiplied by 2 instead of 1.96. In this case, it didn't make much of a difference because I chose a very small standard deviation and a big sample size. And on the plus side, it's going to be 300.2. Like I said, the same thing. It came out to be the same thing almost the same thing. 300.2. Okay, great. So now I call that my confidence interval. And I call it my 95% confidence interval because I used 1.96, which represents 95% of the possible outcomes for the mean, right? Given this,
So what is your margin of error? What is your margin of error then? Is that like
2.156.
it's the number that it's the 1.96 times the standard error. It's the number that you're adding and subtracting. This is the z value or the t value that you're using. This is your standard error. When you multiply them together, you get a number that you're going to add and subtract.
Oh,
So if that number were 5, you'd be adding and subtracting 5 to get the two ends The 5 is your margin of error. Okay, so it's a good name for it, right? Plus or minus, because whenever you say plus or minus, it kind of describes a margin of error. Okay, so we're 95% sure the true mean is between these two numbers. Do we know what the true mean is? No, only that it's likely to be between these two numbers. Do we know it 100% certainly? No, there's 5% chance it could be lower than 295.8 or higher than 300.2, right? Because we're only 95% certain. If I wanted to be more certain, then I would use a Z or T score. I will get to a second which one we would choose. In this case, I'm using Z because I have a very large sample size, right? I use Z whenever I have a large sample size or I know the population standard deviation. Since this is rare, usually using Z because it's a very large sample size. Okay, so if I wanted to be 99% certain, instead of using 1.96, I would use 2.58. And if I look up on my Z table, 2.58, you will see that 2.58, right, represents a situation where you only have 0.5% in this tail and 0.5% in this tail, meaning you got 99% of the possible results between 2.58 standard deviations below and above, and that would give you a larger margin of error. In other words, it'd be 2.58 times 1.1. It'd be basically a little bit more than 5, right? And we'd be adding, subtract that, so it makes it a wider range. Since it's a wider range, it's less likely that the mean would escape us. So now we're 99% certain. If you don't need to be that certain, you want to say you want to be 90% certain, you could use 1.64. Because 1.64 standard deviations is a situation where 5% of the distribution can be below 1.64 standard deviations and above 1.64 standard deviations. 5% on each end ends up to 10% uncertainty, so it's only 90% confident that you capture the actual population mean. And if I use 1.64 instead of 1.96, the margin of error comes out to be a smaller number, which means we have a narrower range. So it's always a trade-off. A narrower range makes you less certain that the true mean is between those two. A wider range makes it more certain that the true mean is between these two. Okay, so now let's take an example like this. And let me see where we wound up here, 295. Okay. I said the width of the strings, yes. I don't know why that opened up. I don't remember asking it to open up, but that's okay. I'm going to be using it in a little while anyway. Oh, I know why it opened up. Good. Let's see. Let's go back here now. Okay, so I'm going to take my sample again. X bar is equal to 298. The standard deviation is equal to 11, and my sample size is equal to 100. Okay, so if I calculate my standard error is going to be equal to standard deviation, I don't know what sigma is, so I got to use that, over the square root of the sample size, which is 11 over a 10, which is 1.1, just as we did before. Okay, so now let's take a look at this. Let's take a look at if the true mean, let's say we knew that the true mean was 300. Right? What's the probability that we would have gotten a value as extreme as 298 if we took a sample from this population? Okay. Well, the actual population was 300. Let's see, my standard error is 1.1. So 298 would be over here. Right? 298. Right? So the difference between 300 and 298 is -2, right? So if I look at this, let's see, X bar minus mu over the standard error gives me what the probability is that I would have a value that's 298 or lower, right? That I would be so extreme that it would be that far from the mean. That's how likely that would be. So it would be equal to X bar, my Z-score, right? The distance from the mean, my Z-score is going to be equal to X bar, which is 298, minus 300 over 1.1. Okay, so how likely is that? That's 2 divided by 1.1. Okay, 2 divided by 1.1. And that means a Z-score 1.81. Okay, good, thank you. Equals, my Z-score equals 1.81. Well, how unlikely is that? My Z-score is negative 1.81. What is that area in here? Well, I can go to my Z table. Okay, so I go to my Z table, and negative 1.81 represents an area of 3.5%, 0.035 I'm going to use. So this area over here is 0.035, 3.5%. You know, it's just as likely if I had taken a sample that I would have missed the mean on the high end as on the low end, right? Just chance that I happen to get 298 instead of 302. So that's 3.5% over here. So a sample that I took that missed the mean by this much might be a little unusual, but it's going to happen. It's going to happen 7% of the time, right? So if I wanted to pick out a spot where I would, what level at which would I expect that I would only see a difference, only see a big enough difference to say that I missed the mean at 95% confidence, right? How far out would that have to be, right? So that would be where this is 2.5% and this is 2.5%. In other words, we can say to ourselves, the likelihood that I would get a mean from this population that was more than 2 standard deviations away, below or above, the likelihood of that happening is less than 5% if I'm willing to go 2 standard deviations out. So I'm going to say to myself, you know, let's test that. Let's see if we can't test that somehow or other. What if I take a sample? Let's say I take, in this case, I was inside of the range for my confidence interval, right? I was inside of the area that would be 2.5% here and 2.5% here, right? The likelihood of getting that far from the true population mean. What if I went to another population? Let's say that these people are, let's say these are males, and maybe the test scores, maybe who knows what they are, right? And then I test 100 females, or I test many females, not 100, but many, say thousands. I test 10,000 females, right? Test the whole population, so that I know that the mean for females is really 299. Okay? Well, gee, the mean for females is 299. The best I can tell you about the mean for males is, remember what it was for 95% confidence interval? I think it was 290, what was it again? It was 303, it was 300.2 and 298.8 or something like that. Yeah, oh, yeah, not 296, 295, 295.8, right? And then and then it was 300.2, right? We're 95% sure the true mean for this population, right, is between 295.8 and 300.2. Okay, well, I don't know what the mean is. We know it's 300, but I don't. The only thing I know about it is I think it's between those two, right? So now, if I want to compare it to females, what was their mean? 299, right? I'm 95% sure the males are somewhere in here. Can I be sure that the females scored higher than the males? Can I be sure that the female score is really different than the male score? I can't, because I don't know the male score. All I know is I'm 95% sure it's between these two numbers. And this number 299 is within that range. So it could be the males could be 299, they could be 300, they could be 300 point, they could be more than 290. Oh, yeah, yeah, but that's okay. That's okay. Don't even bother with the number. It's what I was driving at there is the number is so big that it's basically I measured the whole population. So with the females, there's no question that's what the mean is. So I don't know what that's the mean for females. I don't know the mean for males. It's unknown to me. But I know I'm 95% sure it's between these two numbers. So if I wanted to tell you which one was bigger or smaller, would I be able to? No, because the females, they're within that range there. It could very well be that the males are 299 and they're the same. Or it could also be that the males are 300 and still be within this range, and they're actually their score's a little higher than the females. Well, that's a problem, right? Because if I wanted to show a difference, gee, I can't with this. However, let's look at it a different way. What if I told you that the females scored 300 and 302? Right? I'm 95% sure that the true mean for the male population is between 295 and 300. But I know that the female mean is 302. Can I say that they're different now? I can, right? Because if I'm 95% sure that the male is between these two, and the female is 302, well, I'm 95% certain that they can't be the same. The female has to be bigger, right? Am I 100% certain? No, I'm not, because I'm only 95% certain of what the range is for males. But at least now I can say with 95% certain that these two are not equal. When it was 299, I couldn't say that, because 299 could very well have been what the male mean was for the male population based on the results of my sample, right? So, gee, that's interesting now, because now I got a way to compare two groups. One way to compare the two groups is for me to do exactly what I did here. Okay, is to do exactly what I did here was, for instance, let's say we're going to talk about lead later on. Let's say I'm calculating the amount of air. I take a bunch of samples from blood samples from workers, and the average blood lead level is 10.3, right? And the confidence interval, given the sample size, the standard error, the confidence interval comes out to be 6.4 to 14.2. And I said to myself, oh, these workers, I'm 95% certain that the true mean for their blood lead level is between 6.4 and 14.2. Now, I know that the general male population, workers of people the same age that don't work in this industry, that their mean, right, X bar, their mean, the mean for that other population, all workers that are in different industries, the mean for all of those guys is 7.0. Can I say that these workers have a different mean than these workers do? Yes or no? No, I can't, because it could be 7, right? Because 6.4, my acceptable range, 6.4 to 14. I don't know where the mean is, but I'm 95% sure it's between these two numbers. Well, now what if I measured these guys and it was 3.0? Can I say that the means are different? Well, now I can say that the means are different. I can't say for sure. I can say with 95% certainty that these two means are different. This is basically a single sample test. We're taking a single sample, finding a confidence interval for it, for the mean of the population, and then comparing it to a known value, right? So it makes things simple, because there's only one sample involved there, one standard deviation, and so on and so forth. There's another way for me to do this that's a little bit more elegant, okay? And I'm going to do it. With. Let's see. I'm going to speculate that the way that this works is that let's see, 10.3. Let me go back to the sample. The example I don't want to go back to that. Okay, so X bar was 10.3. I'm going to forget about this. I'm going to come up with my own standard error. I'm going to say my sample size is equal to 100. Sigma is so it's 10. It's going to be 10 divided. I want to get a range of plus or minus 10. It's going to be tough for me to get that range here. Let's see. I guess sigma is equal, standard deviation is equal to. Yeah, you know, these numbers are so small that I'm going to say, I'm going to use something else. I'm going to use some other numbers so I can work with whole numbers rather than very tiny numbers. Okay, I'm going to say, I take a sample, X bar is equal to 500. Okay, my standard deviation is equal to 50. My sample size is equal to 100. And calculate my standard error. It's equal to 50 divided by 10 is 5. Okay, you okay with that? It's equal to 10. So my confidence interval, I'm not going to bother with 1.96, right? I'm just going to say, okay, it's 500 plus or minus, how much is it? Plus or minus 2 times 5 is 10. So it's going to be 490 to 510. Okay, so let's say I compare that. One way I can look at this is I can compare it to a known population and their mean is 480. I know I can say with 95% certainty they're different. If their mean is 495, I can't say with 95% certainty, right? Okay, let's look at it a little bit differently now. Okay, let's forget about this for a second. Let's say that I take this other population, which, let's see, and it turns out that their mean is equal to 500 and 512. Okay, let's see how many standard errors apart the mean that I have is from this mean. Okay, so standard errors, another way is standard errors, and let's say another way of saying number of standard errors is to say Z or T. Right? They're just a number of standard errors apart. Two things are. So Z or T, either way, right? They're both really the same thing. Is equal to X bar minus mu, the difference between the two of those, over the standard error, right? In other words, X bar is what I say was 500 minus 512, right? There's a 12 difference, and the standard error is equal to 5. So that's 12 divided by 5 is 2.4. There's 2.4 standard errors apart. Okay. Now, because it's a big negative, yep, doesn't really matter. That's good. No, negative is good. I'm glad you brought that up. Doesn't really matter. You see, it doesn't matter in a second, but it's good. I like negative because negative is going to be easier for us. Okay, and I'm gonna erase T because I'm gonna use Z because my sample size is so big. We'll worry about T in a second. Okay, so Z is equal to the difference between the two means, and I can't do that now. The two means and the standard error, right? So, okay, if I told minus 2.4 standard deviations apart or standard errors apart. Well, if I go to my T table, if I go to my Z table, rather, my Z table represents areas in a standard deviation, right? In a normal distribution. So I go to my T table. What's the probability that I would get a value that's negative 2.4 standard errors away from the mean? How likely would that happen? How often would that happen? That I would get that big a difference and still be the same mean, right? Okay, let's go to our Z table.
Every time you want to look at like how your percentage of the difference, you look at your value from the Z table.
Well, we're about, yes, at this stage now. Before, we were just using 1.96 to tell whether or not we could be 95% sure they were different or not different. Now we're going to actually look at precisely what is the probability that they're the same or different. How likely it is I would get that extreme a value, that big a difference between the two of them. Okay, so I'm going to go to my Z table. Here's my Z table. So negative 2.40, 0.008, 0.8%. So this area over here is 0.8, 0.008, 0.8%. Well, you know, I could have just as easily gotten a value that was plus 2.4. So there's another 0.8% that I have to account for here, right? Because I didn't know ahead of time whether one group was bigger or the other one was smaller and so on. So total, the probability that I could get that extreme of value below the mean or above the mean and still be from the same population, right? The probability that would occur is 0.016 or 1.6%. Okay, so this big a difference would only occur 1.6% of the time if the two means were the same. If you could say that the two means were the same. Well, that means that I could say that, you know, that if I want to be 95% certain that I'm right, if I say that they're different, if I want to be 95% certain, then really what I'm saying, same thing I'm saying is that I'm willing to be up to 5% chance of being wrong by saying that they're different, right? So what are my odds of being wrong if I say that they're different, if they're that far apart? Well, it's 1.6%, it's 1.016. But I'm willing to tolerate 5% chance of being wrong. So, in other words, I can say, well, it's so unlikely that I would get this sample from this big a difference. You know, if I took a sample from that population, that I would be this is the chances I would get something that far away. If the population had a mean of 510, that given the sample size and the variability, only 1.6% of the time would I get a sample that's so far away from that mean. That means that it's more likely that it was a different population mean. That this came from a population with a different mean. And how likely would I be to be wrong? 1.6% of the time, it could have come from the same population, right? So, in other words, I can use this value of Z, and if my value of Z comes back with an area in the distribution in the Z table, we're going to call that P, probability, that's less than 5%, we can say that they're different. Right, so now that we've decided on that, I'm going to throw a little curve in here, right? And that curve is, well, you know, that was all nice and good when the sample size was 100. What if the sample size is small? What if the sample size is 25? Well, if the sample size is 25, right, instead of using Z, I have to use T, right? And T is different for every sample size. So if I go to the T table.
Do you see because of the small sample size?
Exactly, right.
Okay.
Because remember, this works because we know the population standard deviation. We use the Z table when we know the population standard deviation. We cheat and we say if it's a very big sample, we're going to make believe we know the population standard deviation. If we don't know the population standard deviation, 99% of the time we don't, and it's a small sample size, well then I have to use the T table instead, right? And the difference between the T table and the Z table is that the T table has a larger is a larger value than 1.96 for determining whether these two things are different. In other words, you need to be further away in standard errors to say that they're different, right? And that's the makeup for that extra uncertainty. So let me get the table out, and the T table tells me. Remember, the T table uses this idea. Whoops, got the wrong thing there. Let's see if I can't find it. I think that's it. Exactly. So let's see what we're going to get here. So let's see our T table. So we use degrees of freedom instead of sample size. Same idea, right? Sample size -1. So sample size -1 is 24. So when we work with a small population, instead of saying that we require, in order to be 95% certain, less than 5% chance of being wrong, instead of them being 1.96 standard deviations apart to be able to say they're different, we need them to be 2.064 standard deviations apart. In other words, they have to be further apart. And if the sample size is smaller, like a sample size of 10 would be 9, and that would be 2.62 standard deviations. Instead of 1.96, it would be 2.62 apart instead. That number, this number in this column, we call that the critical value of t. We call it the critical value of t because that's the t-score we have to exceed to be able to say there's less than 5% chance these could be from the same population or populations with the same mean. Okay, so let's go back here and see, what do we say, 2.064. Okay, let's go back here. And what was our z-score? Our z-score was negative 2.4. Is that bigger than 2.064? Yes, it is. So we've exceeded the critical value of t. So even using the t value, we could say that these are different, right? Now, if our t-score, if this has been a sample size of 10, sample size of 10 would be 9 degrees of freedom, 2.64. We'd still be able to say that they're different, right? Because it still exceeds 2.4. What about a sample size of 5? A sample size of 6. Well, our t-score, critical value t, would be 2.57. Now we haven't exceeded it. So if the sample size were only 6, we would not be able to say that these two means are different because we don't have enough evidence that they're far enough apart. Okay, that's the deal with the t-test. But the way we really use it is we actually write it out. We actually write it out as a hypothesis. Okay, so let's do that. Okay, so I'm going to take that same example. X bar is equal to 500. Standard deviation is equal to 50. Now things are going to change now dramatically because of the sample size. N is equal to 25. And the standard error now, based on the standard deviation, is going to be equal to, since it's a small sample size, we have to use the t table, not z table. It's going to be 50 divided by 5, which is going to be 10. Standard error is going to be 10. So our confidence interval is going to be, and I'm going to use 2 for argument's sake, it's going to be 480 to 520. Okay, let's say I'm comparing it to a population with a known mean equal to, I'm going to call it 515. Okay, so what I'm going to say is, before I do this, I haven't done that yet. I haven't actually calculated. I haven't actually done my sample yet. Before I do my sample, I know that this other population has a mean of 515. And I want to sample some other population and compare it to it, see if they got the same mean. Okay? So before I do anything, I say to myself, let's establish a hypothesis. What am I trying to prove? Well, the first thing we're going to do is we're going to assume, to start off with, that there's no difference between the two of them. We call that the null hypothesis. Null being none, nothing, right? So mu for population 1 is equal to mu for population 2. This is population 2. Okay. So I know what this is, right? I know it's equal to 515. I don't know what this is, right? Well, whenever you write your hypotheses out, you always put the mu in instead of X bar because what you're really interested in is the population. You don't really care about the sample. You're really concerned about the population. So that's our starting point. What we want to prove is the alternative hypothesis, that mu1 does not equal to mu2, right? So the next thing I have to do is I have to say to myself, well, what level of significance do I want to apply to this? How accurate do I want to be? Do I want to be 95% certain? Do I want to be 99% certain? Let's say you want to be 95% certain. When we're putting together a hypothesis, we don't express it in terms of how certain we are. We express it in terms of what level of error are we willing to accept. That's called alpha error. Alpha error is the probability that you would be wrong if you say that these are different, reject the null hypothesis, and accept the alternative hypothesis. So if I want to be 95% certain, what would that mean that your alpha is equal to? Your alpha is equal to 5%. You're willing to accept 5% chance of being wrong. Okay? So let's test this now. Let's see if we can say that these two things are different with that level of certainty. So in order to do that, we would have to exceed a T critical. And what is T critical for a sample size of 25? You remember? 2.064. Remember that sample size tells us how far apart these two have to be. Okay, so let's calculate what T is equal to. How many standard errors apart are these two numbers? Okay, so X bar is 500. X bar minus mu over the standard error. That's the number of standard errors, basically. Okay, is X bar is 500 minus 515 over standard error is 10. Okay, and that's equal to 15 over 10, and that's equal to 1.5. Okay, can I say that these are far enough apart for me to say that they're different with only a 5% chance of being wrong? My t-score is bigger or smaller than my t-critical? It's smaller, so I cannot reject the null hypothesis. I fail to reject the null hypothesis. Okay. Let's say that the mean of this thing that I was comparing it to is 525 instead of 515. Let's try it again. In that case,
based on the T-critical value.
What's that?
And you reject it? You reject the null based on the T-critical value?
Well, I reject the null hypothesis based on whether my T value, my T test, the value that I get from my T test, exceeds the critical value of T.
Okay.
It's bigger than the critical value of T. Because what does it mean when it's bigger than the critical value of T? It means that they're so far apart, there's less than 5% chance that they be the same. Okay, so I need that t-score to be big. I need these numbers to be far apart, or I need this number on the bottom to be small, the variability to be small, or the difference to be big. Right? Either one to give me a bigger number. Either one of those would be evidence that they're really different. In other words, far apart or small variability, right, means that they're different. But in this case, I can't say with certainty that they're different because I haven't exceeded that threshold that exceeded the critical value. Well, what if this had been 525? If it had been 525, well, then this would have been 25 and this would have been 2.4, right? Can I say that that mu1 and mu2 are different now? I can because I've exceeded T critical. My T value is bigger than T critical. So my conclusion is I can reject the null hypothesis and accept the alternative hypothesis that they're different. Okay. So what have I done? I've proved with at least 95% certainty, less than 5% chance of being wrong, that this population 1 has a different mu than population 2 does. Am I absolutely positive? No, you're never, in statistics, you're never absolutely positive. But you have a high enough level of certainty to be able to accept this. Okay, so I'm going to do something interesting now. We're going to apply this to an actual data file. And I think I actually have it open already. I think I do. Yeah, there you go. Okay, so here is a data file contains a random selection of births in North Carolina. I think the sample size is like 800 or something like that, right? So I am going to calculate. Let's see what its status. This is the average weight in ounces of births among these 800 pregnancies. Oops, I reopened it again, but that's okay. Let's see, the T ounces, the average. Actually, I'm going to calculate something else. I'm going to use mother's age. It's a simpler number. This is the mother's age. So I'm going to find the average age of mothers, the randomly selected mothers in North Carolina, sample size 800. What the average age for mothers in North Carolina is during this year. I'm going to say analyze. I'm going to go to descriptive statistics, descriptives. I could go to explore it, but I think descriptives will give me what I need for now. And I'm going to say the age of the mother, I'm going to move it into the variables box. You saw what I did there, right? Analyze, descriptive statistics, descriptives. Right? We're going back now. We're going to start using it, SPSS quite a bit more now. We started the semester with it, kind of got away from it when we worked in probability and binomial this and Excel and so on. But now we're going to go back to it quite a bit. So I'm going to go to descriptives. Okay, I'm going to move the variable I'm interested in into the variables box. It's the age of the mother. And I'm going to ask it to calculate for me. Give me the mean, the standard deviation, and the standard error. Minimum and maximum, that looks interesting too. I'm going to click OK. And then I'm going to click OK here, and it's going to come up with the output window. And the output window tells me the average age for mothers in North Carolina is the mean is 26.92, right? That's the average, almost 27, 26.92. And the standard deviation of ages is 6 years, right? So, I can say to myself almost, well, 6 years, 2 standard deviations, 12, 12. The range of 95% of them is 2 standard deviations below, 2 standard deviations above. I can look at that way and so on and so forth. So it's 26.92. Okay, that's based on a sample. That's not all the births in North Carolina that year. Let's say that I were to tell you that in New York State, we track every birth. And I know for the same year, there were 50,000 births, 100,000 births in New York City, and the average age in New York City was 27.4. Right? 27.4. Can I say let's set up a hypothesis. My hypothesis is the average age mu for the mother's age in North Carolina is equal to mu for the mother's age in New York. North Carolina, I only know from a sample. New York, I know the population, right? So there's only one sample involved. Okay, 27, what did I say, 27.5? Okay, 27.5. Okay, so now my null hypothesis is that they're equal. My alternative hypothesis is that they're not equal. I'm not going to guess ahead of time whether North Carolina is younger or older, right? I'm just going to say that they're different. mu1 equals mu, North Carolina equals mu for New York. An alternative hypothesis is mu for North Carolina does not equal mu for New York. Okay, are they different enough for me to say that they're really different based on this sample? So I'm going to go up here to analyze. I'm going to go to compare means. That's what we're doing. Compare means of one population and another. And we have a number of different things we could do. One sample t-test, an independent sample t-test. That means that there's 2 samples. The same thing as saying a 2-sample t-test, 2 independent samples. New York and North Carolina. We didn't take 2 samples, right? We only took 1 sample. So we're back up here by 1 sample t-test, right? There are other forms of this as well. But for right now, this one sample t-test. I'm going to click that, and I'm going to move the test variable is the age of the mother. I'm going to move that in there. But I only have 1 sample, so that's the only thing I have there. What am I comparing it to? I'm comparing it to the known mean for New York State. And that I put in here under the test value. This is what I'm comparing my sample mean to instead. So that's going to be 27 point, what did I say, 5? Okay, 27.5. And I'm going to click OK. And it's going to do a t-test. It's going to run a t-test for me. Click OK. Let's see what we get. We get that the t-score for 799 degrees of freedom, right? The 800 sample size 800. The t-score is negative 2.7. You remember when we looked at the t-table that if it was a degrees of freedom, a sample size of 6, it was like 2.6, and the critical value. If it was 25 sample size, it was 2.06. If it was 100, it was 1.98. If it was 400, it was 1.97. What is it getting closer and closer to? 1.96, right? So you could probably guess, even if we don't have a table, you could probably guess that with that big a sample, the critical value is going to be very close to 1.96. Okay, and what's the t-score we calculated? negative 2.7. Can I say that that t-score is bigger than the critical value of t? It is. So when it's bigger than the critical value of t, what can I say about mu1 equals mu2? I can reject that, reject the null hypothesis that they're the same, and accept the alternative hypothesis that they're different, right? Now, if it had come up 1.6, I would have failed to reject the null hypothesis. That doesn't mean mu1 equals mu2, right? I don't accept the null hypothesis. I only say I failed to reject it, because that's not really what you're trying to prove here. It's not really what this does anyway. So this tells me I can reject my null hypothesis. SPSS takes this one step further. Remember, we looked at how big the tails were when we looked at how far apart the two means were. If you go over to significance, this is the actual probability that you would be wrong if you reject the null hypothesis. And the actual probability is 0.007, 0.7%. So in other words, there's less than 1% chance we would have been wrong if we reject the null hypothesis. That's the same thing as looking at the t-score and saying it's exceeding the critical value. Except when we look at the t-score and say we reject the critical value, we reject it because it's bigger than the critical value, all you can really say is that the chance of being wrong are less than 5%. But over here, because this gives you the significance, two-tailed, it adds up to two tails. Because you have that, you can actually say how probable it would be that you would be wrong. So it's not only less than 5%, it's less than 1% chance of being wrong, right? That's what we learned from this table, right? So this is called a p-value. Another way you could use this table is ignore the t-value degrees of freedom. Just go over here and say to yourself, is my p-value, my probability of being wrong, smaller than alpha, my acceptable level of being wrong? And what was alpha again? 5%, right? Is this less than 5%? Yeah, yes, it's 1%, right? 0.007, not 0.07, 0.007. This is well below 5%. So we reject the null hypothesis because because there's less likelihood we'd be wrong than the level of error we're willing to accept.
But